So this presentation covers box 15.1 and also the associated figure that goes with that. And what box 15.1 is trying to do is get across this idea of the intermediate disturbance hypothesis and the importance of disturbance in ecology in terms of maintaining the diversity, and that applies both to terrestrial, freshwater and marine systems, of course. So basically the idea here is that in environments where there is minimal stress, we will end up with a climax community, one that tends to be dominated by longer lived, less frequently reproducing and slower growing and larger body sized species. These eventually will come to dominate the community and exclude opportunistic species. And the climax community in the diagram is shown on the right hand side. So characteristically the environment would have infrequent disturbance from natural sources of disturbance such as storms, for example, or it might occur a long period of time after a disturbance has occurred, or there may just be very minimal, very light natural disturbances that occur in this environment. Now, as we add disturbance to that system, in other words, we're increasing the disturbance, either the frequency, the intensity, we will start to move the community up the diversity slope. So that might sound counterintuitive, but as we create disturbance in a climax community, we create space for more opportunistic species. So you end up with a combination of slow growing species, but also some shorter lived opportunistic species. And so there's an intermediate disturbance point at which diversity in the system is actually maximized. Now, if we continue to load disturbance on that system, we will then start driving it very steeply on the left hand of the slope, reducing diversity. So effectively what's happening here is we are eliminating the slower growing, long-lived species which have larger body size, and we are replacing them primarily with shorter-lived opportunistic species which come to dominate the highly disturbed community. Now this can be illustrated in the next slide, which shows figure 15.3. And what I've done here in 15.3 is given you an example of an epifaunal community on the seabed and also an infaunal community. So in panel A at the top, this shows the gradient of disturbance from an area that is intensively fished on the far left, and as we move from left to right, the intensity of fishing disturbance decreases substantially. Alternatively, as we move from left to right, this could represent the length of time after a fishing or other physical disturbance has occurred on the seabed. What we see in the highly disturbed area in stage 1 is dominance by small-bodied or encrusting taxa. And gradually, as we move from left to right, with less and less disturbance or a greater period of time after disturbance, we see a greater and increasing dominance by large-bodied fauna, typically slower growing, that have higher levels of complexity and therefore also stimulate communities of higher diversity. Similarly, when we look at the lower panel for the infaunal community, here the disturbance is of a different type. So this is a pollution gradient disturbance. So on the left we have highly anaerobic sediments, for example, as you might find beneath a fish cage on a fish farm in the sea. So basically you've got high levels of organic pollution. This is another form of intense disturbance, and so that community is dominated by a high proportion of small-bodied, fast-growing taxa such as small polychaete worms. Gradually, as we move from left to right, as we move away from the source of pollution, the intensity of the pollution disturbance decreases. This allows larger body size fauna to start to occupy the habitat. Their activities, such as reworking of the sediments, then stimulates other species to colonize and live in that environment, and we transition from a community dominated by small body sized, fast growing polychaete worms to a community which has high levels of diversity and that is dominated by longer lived, slow growing species such as large bivalve mollusks, for example, and echinoderms.